Good morning. So what I am planning to do today is look at some process options for softening. We'll talk about single flow, we'll talk about split flow, and we'll talk about two-stage. So when we talk about single stage, what we're talking about is a system that is only removing carbonate hardness minerals. So we're not attempting to remove the non-carbonate hardness. So we have no soda ash added. We're only adding lime. So when you go back and you think about those reactions, in terms of the reactions, it's the first, because we always have to add lime to neutralize the CO2. The second reaction, which was the removal of carbonate hardness due to calcium, and then the third, which is the removal of carbonate hardness due to magnesium. Now, if we only need calcium removal, then here, the two reactions that are pertinent are 1 and 2. If we need to remove magnesium, then we need to raise the pH to 11.3, and that is to precipitate the magnesium hydroxide. So because the solubility of magnesium carbonate is still quite high, we need to shift that equilibrium to form magnesium hydroxide. And here we're looking at reactions 1, 2, and 3. Now we can also use a two-stage, and in this case, in both the previous case and in this case, the entire flow is being treated. So in the first stage, we're adding lime, and then we're adding soda ash in the second stage. So we're looking at removal of carbonate hardness in stage 1. So again, we're looking at reactions 1, 2, and 3. And then in the second stage, we're looking at removing the magnesium hardness. So we're looking only at stage 5. So we're looking at the removal of non-carbonate hardness due to magnesium. We're only adding soda ash. In both cases, shown here, we only need a pH of 10.3 for reaction 5. So what is shown here is that we add CO2. So if you remember, when we add CO2, it reacts with water to form carbonic acid. And that carbonic acid will lower the pH. So we lower the pH from 11.3 to 10.3 here, and we still need to lower the pH further because we can't distribute water at a pH of 10.3. The maximum we want to distribute is about 9.2. So in this case, CO2 is again added in order to lower the pH. So here, what you would want is a pH between 8 and 9 as your final pH. Now we can also operate at a split flow, and here you're not treating the entire flow. This is the process that Lansing, if we were to go to the Lansing dye plant this year, this is what we would see. So what they do is they add lime in the first stage, but they don't treat the entire flow. So they're treating some fraction of the flow. They bypass some fraction of the flow. They then mix that here, and they treat the entire flow. So we're treating the entire flow through the second stage. Now we do this because we don't need a water with 40 milligrams per liter of calcium carbonate. 40 milligrams per liter comes from the practical limits. So we can tailor a water to have about 40 milligrams per liter of magnesium hardness. That's kind of an ideal. It's a rule of thumb. It's essentially a water that isn't going to produce significant problems with scaling on the hot water heaters, scaling in the valves, etc. So this reduces the capital costs because we don't need as big of a stage 1 tank. It reduces operational costs because it reduces the amount of sludge that we need for stage 1. And if it reduces the amount of it reduces the amount of chemicals we need for stage 1. So it's reducing the amount of lime that we need to add. It also reduces the amount of sludge we produce. So you get a double benefit. And then the other thing that it does is it uses the natural alkalinity in the water to adjust the pH. Notice here, there isn't a recarbonation step between stage 1 and stage 2. And the reason for that is we're using the alkalinity in the raw water to provide additional alkalinity and to adjust the pH. So in this case here, we add lime in stage 1. We may add lime in stage 2, or we may just add soda ash, depending on what we're trying to remove and in terms of the water quality. The operational pH is 11.3 in stage 1, just as it was before, and 10.3 in stage 2. And what we will do is we'll adjust this bypass. So this X is the bypass ratio. We'll adjust that based on the hardness levels. And we use magnesium as our criteria. Okay. So what we're doing is we'll soften the water to practical limits in stage 1, but we're not softening all of the water. We'll then blend the raw water with the treated water, and then we'll treat in stage 2. Okay. So if we treat to practical limits, the magnesium concentration from stage 1 is 10 milligrams per liter as calcium carbonate. Where did that come from? What's the source of that 10 milligram per liter concentration? The 10 milligram per liter concentration comes from the solubility limits for magnesium hydroxide. It also takes into account that precipitation reactions are not instantaneous, so we actually don't achieve equilibrium in the treatment process. And we have potential short-circuiting, so not all of the water may reside in the tank for the design hydraulic detention time. So this here we will refer to as the initial magnesium concentration, because it's the initial reaction level. It's our solubility limit. Mg final is what we achieve here. So Mg final is what we achieve from the second. It's the effluent from the second stage. And Mg raw is our raw water magnesium concentration. Notice here, we assume that we have no additional magnesium removal during recarbonation. We assume we have no additional magnesium removal during filtration or any subsequent process. So what I'm going to have you work on, I'm going to put you into breakout groups, and I have a PowerPoint that you can work on, is this problem here. Okay, so you've been hired to design a water treatment plant. I've given you the design flow, and I've given you a pH. Concentrations are different from what we used on Wednesday. So I've given you the concentrations of CO2 in the water, alkalinity, chloride, calcium, sodium, and sulfate. Notice all of the concentrations are in milligrams per liter. The objective is to soften the water to achieve a magnesium hardness of 40 milligrams per liter. The total hardness of the finished water must be in the range 80 to 120 milligrams per liter as calcium carbonate. So you'll use split treatment to achieve this goal. What I want you to do in the breakout groups is to begin this process. I want you first to draw a bar graph. I want you to calculate the total hardness, the carbonate hardness, the non-carbonate hardness. I want you then to start thinking about how much lime, how are you going to determine the lime, what reactions are pertinent. I don't want you to have to go, you don't have to go through the calculations, but I want you to start thinking through this process. And I'm hoping, and then we'll go back and we will evaluate and work through this problem. We won't finish it today, we'll finish it on Monday. So let's go back, look at the problem here. And so what I've done is I've given you, as I mentioned, the concentrations of each of these species. So let's just start with looking at hardness. So you were given the concentrations of CO2, calcium, magnesium, sodium, sulfate, and I'm just going to switch over here where I can see. I don't have everything written down. Chloride. Okay. So this is 12.5, and I gave you all of the concentrations in milligrams per liter as calcium carbonate, so you didn't have to do the conversions. And then calcium's 238, and magnesium is, just realized I didn't give you the magnesium concentration. Let's go back. I apologize. The magnesium concentration is, I have it written down, but I don't have it calculated. It's 90 milligrams per liter. Sodium is 56.2, and sulfate is 76, and chloride is 95.6. Okay, so now we have all the concentrations, which would have been helpful before. So to calculate the total hardness, the only ions we have that are polyvalent are calcium and magnesium. So we'll add those. We have 238 plus 90 equals 328 milligrams per liter as calcium. That's our total hardness. pH is 7.3, and you were given an alkalinity of 198 milligrams per liter. So if my alkalinity is 198 and my total hardness is 328, what is my carbonate hardness? Which of those are limiting? So alkalinity is limiting. So my carbonate hardness is 198 milligrams per liter as calcium carbonate. And my non-carbonate hardness is equal to 328 minus 198, or 130 milligrams per liter. Now, because our pH is 7.3, we can make the assumption that my alkalinity is approximately equal to the bicarbonate concentration. So if we draw the bar graph, start here at 0. We always write the CO2 as a negative to 0, and it is 12.5. That's what we were given. Calcium is 238, so this is our calcium. Magnesium is 90. So this is going to be, notice I'm adding. So think of this as cumulative concentrations. And then the sodium is here. So these are all of the cations that you were given. My bicarbonate concentration is 198. My chloride concentration is 95.6. So this is going to add up to 293.6. And then my sulfate, when I add that, it's 396. So this is sulfate. There's obviously some, the way this is drawn and the data that's given, there are some non-analyzed or reported cations. So for instance, this could be potassium, could be barium. Those are not recorded. So this is our bar chart. Now, when we start wanting to think through those reactions, this portion here that I've shown in yellow corresponds to what? The portion in yellow corresponds to what? It's carbonate
hardness.
Exactly. It's carbonate hardness due to calcium. The portion that I highlight now in blue here corresponds to what?
Non-carbonate hardness due to calcium.
Exactly.
So the magnesium is not included in the non-carbonate hardness?
It's not included in the carbonate hardness. So notice there's no overlap. We always draw these in terms of the highest concentration to the lowest concentration. So calcium's almost always going to be first, followed by magnesium, and then usually followed by sodium. For your anions, bicarbonate, it's typically going to be the anion in the highest concentration, so that will typically be first. And then chloride and sulfate they could vary depending on the water. So now let's look. So now if I take this portion here, so if I take this portion here in green, that corresponds to what?
Non-carbonate hardness due to magnesium.
Exactly. Now, once we have that, we can start thinking through the reactions. So the carbonate hardness due to calcium corresponds to what reaction? For our softening reactions, what reaction does that correspond to? It's going to be reaction 2. The blue, okay, their non-carbonate hardness due to calcium corresponds to reaction 4. Non-carbonate hardness due to magnesium corresponds to reaction 5. Okay. What about reaction 1? The CO2.
Just the neutralization of CO2.
Exactly. So that's the neutralization of CO2. So that corresponds to this. That CO2 concentration will then govern reaction 1. What about reaction 3?
That shouldn't be involved in this one.
So reaction 3 isn't involved because we have no carbonate hardness due to magnesium. So what you're doing, it's really bookkeeping, or think of it as a, kind of an accounting problem. What you're doing with all of these problems is really keeping track of what is present and how those ions interact, and then those reactions that are pertinent based on that water quality. I'm going to rewrite our concentration. So we have CO2 as 12.5 milligrams per liter as calcium carbonate. Our calcium is 238, magnesium 90.6, sodium is 56.2, alkalinity is 198, chloride is 95.6, and sulfate is 76. So let's write out each of our reactions. The first reaction, we have CO2 reacting with lime to form calcium carbonate. We have 12.5 milligrams per liter as calcium carbonate. But we need our concentrations in molar units. So how do we go from molar units, from milligrams per liter to molar units? What we want is we'll do it in millimoles per liter. So this is what we want, because stoichiometry is typically written in moles per liter. So we're going to divide this by the molecular weight of calcium carbonate. So that is 100 milligrams per millimole. Happens to be really convenient. So we have 0.125 millimoles per liter of CO2. For the reaction, this is reaction 1. Reaction 2 is carbonate hardness due to calcium. So we have calcium plus 2 bicarbonate plus calcium hydroxide produces 2 moles of calcium carbonate plus 2 waters. So we said that we had our carbonate hardness, let's go back. Our carbonate hardness due to calcium here is that yellow portion, so it's 198. So we have 198 milligrams per liter as calcium carbonate. So if it's 198, what is the concentration in millimoles per liter? Divide by 100, and that's 1.98 millimoles per liter. So just looking at those two reactions, how much lime do we need to add for that first reaction? 0.125 millimoles per liter. So the liter will actually end up corresponding to our flow rate. We'll talk about this. So for the second reaction, how much lime do we need to add? 1.98 millimolar. So we said we didn't have reaction 3. So reaction 3, we don't have to worry about. Looking at reaction 4. So this is calcium reacting with soda ash to form calcium carbonate plus 2 sodiums. And we have, we go back here, that's this portion here. So that is 238 minus 198, so that's 40. So we have 40 milligrams per liter as calcium carbonate, which corresponds, divided by 100, and that is 0.4 millimolar. How much lime do we add? So how much lime do we add in reaction 4?
Isn't that for soda ash?
None. 0, right? We add soda ash. And the last one is reaction 5, and that is our non-carbonate hardness due to magnesium. So we have magnesium plus lime plus soda ash. And I'm not going to further add the rest. Okay. So we have all of our magnesium is present as non-carbonate hardness. So we have 90.6 milligrams per liter. Divide that by 100. 0.906 millimolar. So we need, for lime, we need 0.906 millimolar. For soda ash, 0.906. So the total lime is equal to 0.125 plus 1.98 plus 0.906, and that is equal to 3.011 millimolar. And my total soda ash is equal to 0.4, that's 0.906, and that is equal to 1.306. So we'll stop there. My suggestion is over the weekend, look back over this, see if you can determine the split ratio, and then think about how do we move forward. We've only looked at stage 1 now, so we need to begin to look at stage 2. So let's end here, and I'm happy to take